So thank you for the introduction, thank you for the invitation to come to the conference to give a keynote presentation, and thank you for telling me that it had to be on the topic of limitations of pure tone audiometry. As audiologists, we love pure tone audiometry, but I guess the question is, do we potentially love it too much? So when we go back to clinics on Monday, how many audiograms would a typical audiologist carry out? I'm sure there's wide variations, but let's say the typical audiologist will do 5 audiograms on Monday, and we do that every day of the week. So that's 25 audiograms that each audiologist will do next week. And let's say we do that for 40 weeks of the year. That's 1,000 audiograms. And let's just say our career lasts 40 years. That's 40,000 audiograms. So you have to love something a lot to want to do it 40,000 times, right? But sometimes love is blind. And sometimes we don't appreciate that despite the things we like, there are some things that maybe we could do differently or we could change. So every relationship comes with ups and downs. And I think the relationship between audiologists and pure tone audiometry is the same. We have our ups and downs. Actually, we have our 5 up, 10 down in the jargon that we use. But I'm going to talk about a different 5 up and 10 down today. I'm going to talk about the 5 up in terms of what are the 5 positives about pure tone audiometry, and then we'll look at 10 downs or 10 of the potential limitations. So we are all audiologists, so I don't need to spend a lot of time talking about the positives. We use it because we can quantify hearing level, we can obtain ear-specific information, sight to lesion. Sometimes there's something about the audiometric configuration of pattern that helps explain the nature of the cause of the hearing difficulty, and it has universal application. Relatively cheap to do, easy to calibrate, simple tones used across the world. So let's move on to the bit that you asked me to talk about, and that is, what are some of the limitations of pure tone audiometry? Now, the first one is not so much a limitation, more an irritation, that we're one of the few groups that can't get the scientific convention right with graphs. Graphs normally start with small numbers in the bottom left corner, and then they get bigger as you move along the x-axis and bigger as you go up the y-axis. And we do things upside down with the audiogram. And it all started round about 100 years ago when we started to use pure tone audiometry, when Fowler, an otologist, provided us with one of the first audiograms, but on the y-axis he called it percent of normal hearing. And if you like, later I can explain how you take a threshold and you change it to percent normal hearing. But this would follow the normal scientific convention that the further up the graph you are, the better your hearing is. But then along came Fletcher, a physicist, who said, I don't like this idea of changing things into a percentage of normal hearing, so let's look at sensation loss. Let's compare ourselves to a reference value and say, how different is this individual from a reference value? And we've now gone from sensation loss to decibel scales in terms of hearing loss, and now the correct term is decibels in terms of hearing level. But the one mistake that he made was not to reverse the axis, so small numbers are at the bottom. So the audiogram format that we use today can be traced back to Fletcher in 1923, and for that reason, we've been doomed forever since to use this graph that's upside down. That's just an irritation. Let's think of some of the potential limitations. What about the airborne gap that we repeatedly find at the higher frequencies in individuals such as adults who come along with an age-related hearing loss, and we're not expecting there to be any element of a conductive hearing loss? This is not an uncommon finding, right, at 3,000 hertz and 4,000 hertz. And what we're all trained and told was that this is airborne sound that radiates off the bone vibrator and it goes into our ear canal, and we're responding to air conduction sound. So the British Society of Audiology, in the recommended procedure, says stick an earplug in the ear when you're doing bone conduction thresholds at high frequency, and that'll solve the problem. And actually, it rarely solves the problem. So for that reason, we rarely take the trouble to put an earplug in when we're testing the higher frequencies. The most likely explanation is the calibration value for bone conduction at 4,000 hertz is wrong. And if you look at the graph on the left-hand side, this is showing the airborne gap unexpected airborne gaps in individuals who are assumed to have normal hearing or a sensorineural hearing loss. And as the hearing loss becomes more severe along the x-axis, the airborne gap at 4,000 hertz increases for reasons that we can't quite explain yet. So it seems to be very common. And the explanation, I think, is if you look at the graph on the right-hand side, for each of the audiometric frequencies, it shows you the reference value that's used when we're calibrating our audiometer for bone conduction for 0 dB HL. And you'll see that there's a remarkably linear relationship between the reference force level we use at 250 hertz and 500 and all the way along. And then something happens along here up at 4,000 that we're not actually on the line. And that difference there is of the order of about 15 decibels, which is remarkably similar to the sort of airborne gap we frequently get at high frequencies. So the solution is that we should, until the standard is corrected, add 15 decibels every time we measure bone conduction at 4 kilohertz, and we can all go away and we can start doing that from Monday morning, right? Good. Actually, limitations 3, 4, and 5 are all things that I've discussed before at BAA conference, so if you forgive me, I'm not going to spend a lot of time explaining them all. I'll just make a passing comment. First one is the audiogram and the reference values are based on adults who have average size ear canals. And if you're not an average adult, then the decibel hearing level scale doesn't work. Here's data for a 9-month-old child who has a much smaller ear canal than adults. And depending on what transducer you use, you're liable to get a different value. The best ones are obtained with insert earphones, and that's because we put an insert earphone into a small ear canal because the volume is much smaller than an adult. For a particular audiometer dial reading, a higher value reaches the eardrum. So we don't have to turn our audiometer dial up so much to get the threshold value at the eardrum. So it's all an anomaly because of the small ear canal. And for that reason, when you have someone who isn't an average adult, and I'm thinking particularly of young children here, we need to take account of the ear canal acoustics in our audiometric data, not just for our hearing aid data, but also in terms of audiometry. Otherwise, the potential danger is, with a small ear, you start up here, and as someone gets larger, and their ear canal gets larger, we have to turn our audiometer up further, and it would start to move down and look like the individual has a progressive hearing loss. Somewhat related is that when we're working with hearing aids, we really want to know about the precise interrelationship between the different variables. We know we have the audiometric variables measured in HL, that's the green area on this graph here. We want to know what happens with primarily speech before it's amplified, that's the blue one down here. Is it audible, is it not? And once we've provided amplification, we want to know where is the amplified signal in the dynamic range. You just simply can't do that with a pure tone audiogram. We can only do it with this sort of graph because everything's in the same units, sound pressure level. And actually there's the apple and oranges because you can measure the hearing aid in sound pressure level, but it's in a coupler. You can measure speech arriving at someone's ear. It has a different reference value in the sound field. So the one way of doing it, and to people who work in pediatrics in particular, we're very familiar with this, is once we've established there's a hearing difficulty and we're going to provide amplification, is to put the audiogram to one side and convert everything and use it on an SPLogram. And the third thing that I've presented before actually was a keynote presentation at our very first BAA conference in Manchester, is cochlear dead regions. So the analogy for a cochlear dead region is you have a piano keyboard and you hit the key, you strike the key, but the string's not attached, so you strike it and you don't hear anything. But if you give it a very hard thump, the strings at either side might jangle, so you do detect something. Not what you meant to detect, but you do detect something. And that really explains cochlear dead regions, that you can measure a threshold and plot it on a pure tone audiogram, but it may not be the response of the basilar membrane at the correct place for the frequency that you've been using. It's because you've used a high enough level and there's been some jangling or vibration at either side. So actually the person would have no hearing at the frequency of the dead region. But when you use a high sound level, you get the jangling at either side. And we've carried out many studies on this. A lot of them recently came from Anna Pepler's PhD, and one of the studies showed that for the typical adult that comes along to the NHS for a hearing aid, around about 1/3 have evidence of a cochlear dead region. Not an extensive dead region, but evidence all the same, maybe just at 4,000 hertz, maybe at 3,000 hertz. And the question really is, well, who cares? Does it matter if there's a cochlear dead region at these frequencies? Will it change things that we do in terms of our rehabilitation and hearing aid fitting? And that's what's summarised in this slide here, where we've taken two groups of individuals with very similar audiometric thresholds, but one group has dead regions at high frequency and one group doesn't. And they've been provided with a hearing aid matching a normal prescription. It was NAL-NL1 at this time. And then we said, well, what would happen if we didn't bother amplifying past 3,000 hertz? What if we just stopped at 3,000? If it's a dead region at 4,000, it means there's going to be less chance of acoustic feedback, less time spent trying to match a target. So on the left-hand side, we measured performance listening to speech in the quiet. And irrespective of whether the individual had a dead region or not, the difference between the normal hearing aid fitting and limiting it to 3,000 hertz was about 5% difference on this speech test. So you got an extra 5% on this lab-based speech test if you amplified as best you could up to 4,000 hertz. We then did the test in background noise, and if you don't have a dead region, it's a lot more challenging to hear in background noise, but the individuals got something approaching 15% better performance in noise if we amplified all the way up to 4,000 hertz. The individuals with a dead region didn't get the same benefit at all. They didn't do worse. So the evidence isn't we shouldn't provide amplification. The evidence from this study at least, and some other ones that have been published, is that individuals with dead regions may not get as much benefit in background noise as people who don't have dead regions. And that, of course, could be important. We might not be setting our hearing aid up any differently, but important for counselling purposes. So the solution there would be to do a spot check, just at a high frequency, 3,000 hertz or 4,000 hertz, to look for evidence of a dead region. And that's also something that you're going to go away and do from Monday, right? Okay. Is it possible that there could be hearing disorders that we can't identify on the pure tone audiogram? I want to mention one condition called cochlear synaptopathy, and it's sometimes referred to interchangeably as, some people anyway, use it interchangeably with the term hidden hearing loss. And the current interest comes from this study on mice by Kujawa and Lieberman that was published in 2009. Mice were exposed to noise and they had a temporary threshold shift. Their thresholds were measured using ABR, not a behavioural test. So there was an elevation of threshold, temporary elevation, then it returned to normal. But what these researchers noted was that if you plotted the ABR for different input levels, we expect the amplitude to grow. But in the animals that are exposed to noise, the amplitude didn't grow so much. So although their hearing threshold had returned to normal, there was something different about the number of neurons potentially firing, or maybe having less neurons firing, that when you use a high input level for your ABR, you're not getting as big an amplitude. Now, you would miss that on a pure tone audiogram, but if there are less neurons available to code superthreshold deficits, maybe that could explain why some people, at least in part, have difficulty with speech and background noise, or why some people have tinnitus. So that might be the relevance to us. And the mechanism really is that we have our inner hair cell, which transduces vibration on the basal membrane into an electrical signal to go up the hearing nerve. You present some damaging noise, and that damages some of the synapses that joins the hair cell to the neurons. They're not completely damaged, so you're still able to record and get a response down at normal threshold level. And over time, some of these neurons die back as well. So you can have a normal hearing threshold, but fewer neurons firing. And these tend to be the neurons that code higher sound pressure levels. So the neurons are working that would record quiet sounds for threshold, but they're not all there and working for the higher level. So is there evidence of cochlear synaptopathy in humans with noise exposure? Well, the evidence right now is somewhat mixed. Here's studies that have looked at the auditory brainstem response and the amplitude of wave 1 from the auditory nerve in humans. Stamper and Johnson were the first group to do this, published last year, and they said, we've got evidence that the more noise exposure, the smaller the amplitude on the ABR. They've since followed it up with a letter to the editor to say, actually, when we look at the data more closely, that seems to happen for women, so not for men. So not quite as clear-cut as it first seemed. In Manchester, there's a very large MRC 5-year programme grant, and the principal research investigator for that is Chris Plack. That work's just been published. Hundreds of individuals with different amounts of noise exposure. We couldn't find evidence for that. But then another study just published by Lieberman using electrocochleography, so looking at just the equivalent of the wave one in the ABR, says, actually, we get a different wave one for high noise exposure versus no noise exposure. And actually, the ones with more noise exposure, the participants, also perform more poorly in noise. So at the present time, the jury is out on the existence of cochlear synaptopathy or hidden hearing loss in humans. But here are some other examples. This is currently unpublished data that comes from Manchester from a PhD study looking at individuals with diabetes. So people who are diabetic have peripheral vascular problems that affect lots of things, including their vision. And it would be surprising if it didn't affect hearing. And yet, you'd be hard pushed to find evidence that it changes someone's hearing threshold on an audiogram. But here's data from individuals who have normal audiograms, one group who are diabetics and one group who aren't. And on the left-hand side, we have a speech and noise test, and the red block are the individuals who are diabetic. And further up the graph means they needed a more favorable signal-to-noise ratio to be able to get the same performance as the control group. So they have more difficulty in background noise. And on the right-hand side, using self-report, this happens to be the SSQ hearing scale. If you look at the red block, and again, a low score means more problems. And there are other data from this study that I'm not sharing with you today, but multiple evidence that individuals can have normal audiograms, but there are hearing deficits that show up on other measures. So a normal pure tone audiogram, we shouldn't be mistaken for thinking that means someone's going to have good speech and noise ability. Is it possible that there could be a normal audiogram, but there's a hearing loss at the higher frequencies, at extended higher frequencies that we don't normally measure? And indeed, that is the case. There's lots of evidence out there. And I'm going to give you two examples today, one from an adult study and one from a pediatric study. So here's our hidden hearing loss adult study from Manchester. And as individuals' noise exposure increase, their hearing levels at 16,000 hertz increase. That's the black line. Hearing on average is poorer at the higher frequencies if you have more noise exposure. Actually, if we looked at the subtleties, we find that that relationship is strong for women, but not so strong for men. So that suggests that there may well be a sex difference in susceptibility to noise exposure. Could agree with the Johnson and Stanford paper that said, actually, we've noticed this difference on male and females. Looks like females are potentially more vulnerable, but you wouldn't detect that on a normal pure tone audiogram that goes up to 8,000 hertz. So the solution there is we would need to test at extended high frequencies to look for early evidence of damage, and that could be very important for noise exposure, or it could be for ototoxicity, for example. Here's the pediatric study. This is a comparison of children who don't have a history of otitis media with children who had a former history who have a history from former exposure to otitis media, but not at the time of testing. These are very high frequencies, 9,000 hertz up to 20,000 hertz, and it's measured in SPL. So there are two normal hearing groups, different age groups, and these are the two symbols up the top. That's our control, or our reference values, our equivalent of 0 dB HL for these high frequencies. And these other two sets of symbols are the children who are now, and have been for some time, completely free of otitis media, but actually they have poorer high frequency hearing. And interestingly, over time, the older age group, their hearing has deteriorated more. This study, I should have said, comes from Lisa Hunter at Cincinnati. So here's evidence that children who formerly had otitis media and are now free of it are left with a high frequency hearing loss. And actually, David Moore, who's known to many people here currently at Cincinnati, now has evidence to show that a sizable number of children who are labelled as having auditory processing disorder also have poor hearing at these extended high frequencies, but a normal audiogram up to 4,000 hertz. So the solution here would be to test extended high frequencies to help understand unexplained problems. So is that feasible? Are we able to incorporate extended high frequency testing into clinical practice? Well, all audiometers in the UK will allow you to test up to at least 12.5 kilohertz. The standard for calibration for high frequencies is this thing called 389 Part 5. But actually the earphones that are used in that standard are pretty much all obsolete. However, there are groups that have published data in peer-reviewed literature for higher frequencies, extended higher frequencies, for earphone models that are currently available, and there's data, for example, for this one, Sennheiser HDA 280. And the 389 Part 1, the normal standard used to calibrate up to 8,000 hertz, is being updated. That will very likely go up to 12.5 kilohertz, so we will be able to have reference values to go all the way up. But the data exists in publications, so actually the solution is to go out and buy a pair of HDA 280, I don't mean now in my presentation, but soon, on Amazon for £100, and then your audiometer can be calibrated up to 12.5 kilohertz, and you can use it to solve some of these problems that I've just listed on the previous slides. Number 8, misuse of audiometric descriptors. And I think this is probably the reason why I was invited to do this presentation, primarily because of the interest in some clinical commissioning groups to use the audiometric descriptor as the sole determinant of hearing aid candidacy. So the British Society of Audiology has these descriptors, mild, moderate, severe. It's not standardized. There are other organizations, I've listed ASHA and the World Health Organization here, who use different terminology. They might use slight, they might use mild, they might take an average over different frequencies. But we have to be careful not to shoot ourselves in the foot by relying too much on these descriptors of impairment from the pure tone audiogram. And here's data that comes from Glasgow from the Institute of Hearing Research, and I'm grateful to Bill, who's in the audience somewhere, for this graph that he put together for me to share with you today. Very large number of participants, roughly 100 in each of these groups, people with hearing that averages between 0 and 10, 10 to 20, 10 to 30, all the way along. And one question from the Glasgow Hearing Aid Benefit Profile: how much difficulty do you have with group conversation? And if you're on the left-hand side, on the blue colours, you're not reporting much difficulty, and as you move across to the red ones, you're reporting a lot more difficulties. It goes from none, slight, moderate, great, and cannot. Just for example, look at individuals whose average hearing thresholds fall between the 30 to 40 dBHL. That's classified as mild by BSA for the audiometric descriptors. 84% report at least moderate difficulty in background noise. 84%. In fact, if you go to the 20 to 30, 63%. And if you combine the 20 to 40 dB group, 75% of these individuals will report at least moderate difficulty in background noise. That puts a very different slant on saying this individual has a mild hearing loss. So we mustn't confuse pure tone audiogram descriptors with the consequences, the severity of the consequences that an individual has. And actually there are other studies that support that one there. So around about a year ago, I was able to add a comment to the BSA recommended procedure beside these audiometric descriptors. And the start of the comment reads like this: while audiometric descriptors may provide a useful summary of an individual's hearing threshold, they shall not be used as a sole determinant for the provision of hearing support. And then it goes on to explain why that is the case. And actually I've spoken to some other organizations, and the World Health Organization have agreed to use the same wording or similar wording on their audiometric descriptors on their website. And we have Ian Winwell here, from president of AAA, so maybe we can chat with Ian and see if in the States we can get people to incorporate this wording so that we're not misleading people by using these audiometric descriptors. So the solution really is, we're going to identify impairment on an audiogram, but if we're really interested in the consequences, particularly for rehabilitation, then we have to measure the consequences. And the one example I've shown you here is taking that question from the Glasgow Hearing Aid Benefit Profile and doing that for each individual. But even today, we're able to report to people who are interested in these audiometric descriptors that individuals who fall in the mild category, a diagnostic category for clinical purposes, 75% have at least moderate difficulty in background noise. Moving on to number 9 of my list, the pure tone audiogram only partially predicts the challenges of listening to speech and background noise. If it was a perfect predictor, as we move along hearing level here, we'd have a straight line going up here, signal to noise ratio for criteria performance. And actually, there's a lot of spread there. So that tells us it's more than just audibility. When this work was published, the explanation was, the distortion, the other things that's gone wrong in the auditory system. We now know that it's more than that. Here's a recent study that's compared 2 groups of participants, young normal hearing, older normal hearing. And if you look at their performance to speech in the quiet, both groups do well. If you start to add background noise to the speech task, performance comes down. But you'll see the black dots are the older group, and their performance falls further. So there's something that explains a difference between young and old people despite normal hearing thresholds in an audiogram. And the explanation from this study is a number of factors, one of them being cognitive ability. Our brain processing, our ability to solve problems and remember things predicts an individual's performance. So factors other than audibility influence hearing in background noise. So just coming to the last point, when I was preparing this presentation, I was thinking of this old film, this religious comedy film about the life of Brian, where the cast are talking about, what have the Romans ever done for us? And the quote is, all right, apart from better sanitation and public health and roads and a fresh water system and baths and public order, what have the Romans done for us? And the answer is, well, brought us peace. So, what would Python say for the life of the audiogram? All right. Apart from ear-specific information and quantifying hearing level and identifying site of lesion and the nature of loss and universal application, what has the pure tone audiogram done for us? Well, you might say, it's provided the information for the hearing aid prescription. That means it's untouchable. Except, we're just on the cusp of a diminishing role for pure tone audiometry in hearing aid prescription work. The current model is that we have the audiogram, we enter these values into the manufacturer's software, we get a click and fit match, we use Relay measures to improve the match. That's what we currently do. Now there are individuals looking at self-fitting devices that you determine if somebody is likely to be a candidate, and then you let the individual do the corrections and the adjustment of the device himself. And in this study, and this work comes from Diane Fantassel, a blinded study where individuals get to compare the settings that they've set the device to compared to NAL, NL2. The green ones, 75% say that their preference is for the one that they've fitted themselves. Is blinded, so they don't notice their one. And this is the sort of study that's now lending support for over-the-counter products. Some currently available, not all going to be widely available by Monday, but this is the future. So thank you very much for inviting me to come and do the keynote presentation. The purpose of a keynote presentation is to establish the framework for a conference and to look at the prevailing themes. So we have to be careful not to throw out the baby with the bathwater. We realise and accept there are advantages to using the pure tone audiogram, but the slightly more controversial part that I want you to remember and take away is that we need to be aware of some of the limitations of the pure tone audiogram. We have to seek out opportunities to modify what we currently do, and also, because we're healthcare scientists and critical thinkers, to acknowledge that there are ongoing uncertainties. Thank you very much for your attention.